Hello. Thank you all very much for coming. I see some people are still filing in, but I'm going to go ahead and get started. My name is Doug Hawkins. I am one of the lead JET developers at a company called Azul Systems that makes a couple different virtual machine products. One that's rather custom, but we also have an open JDK implementation. I'm going to stick to just talking about HotSpot today, but this is going to be the mechanics of what goes on inside the VM. At a high level, what we're going to do is look at what happens when your Java code runs. This is sort of a simplified view of what occurs. You're going to start off running in the interpreter. Then we'll do some profiling. Maybe we'll do that interpreter. Maybe we'll do that in a just-in-time compiler. Then we'll do some just-in-time compilation after we found a method is hot. And yes, it's actually possible to start this cycle over again. You can just-in-time compile something or deoptimize a piece of code and start the cycle again under certain circumstances. And we're going to look at why all of this stuff happens. To be a little more concrete, we're going to look at what triggers the just-in-time compiler, when it triggers, why maybe an ahead-of-time compiler isn't a great solution for Java, or at least the pros and cons of ahead-of-time compilation versus just-in-time compilation, what causes the unjitting, the deoptimization, and some about what impact this has on you. So, what triggers the JIT? We're going to start with a very simple program. I have a main here. It constructs an array of random integers, 5,000 of them. And then I'm going to measure how long it takes to do this summation inside this loop. You can probably guess what the sum function looks like. And I'm going to measure that with system nanotime. For good measure, I'm going to assign this value, the result of sum, to a global variable just to make sure the just-in-time compiler doesn't get too clever and optimize this away. If I didn't do that, in fact, we'd end up measuring nothing. So I'm going to run this program, and we're going to see the table of numbers that it produces. So here's the program in its entirety. There's the sum function. There's the random int generation. And now it's running. And the first few iterations of the outer loop are going to happen in the interpreter. So that's where we're seeing these 75,000, 70,000-ish nanoseconds to do the summation of our 5,000 ints. As we continue to run, the numbers start to improve. You can see somewhere around iteration 13, 14, we get better. We get to about 12,000 nanoseconds. That is the first just-in-time compiler kicking in. As of Java 8, we have what is called tiered compilation on by default. So there's not actually one just-in-time compiler, but two. So if we keep running, we'll see these 10,000-ish nanoseconds for a little while. And then it'll improve further to about 1,700 nanoseconds on my laptop here. OK, so that is what happens when you run the code. As the code gets hotter, it goes through more and more tiers of just-in-time compilation. And we can plot it like this. And you can see interpreter was running for about the first 12 or 13 iterations. Then we went and improved some, ran in the first tier JIT. This benchmark is actually a little unstable for some reason. And then it settles down once we get into the second tier JIT. And this is pretty normal for any program. What's a little abnormal about it is it looks like this perfect step. It's because it's a very simple program. It's composed of basically two functions that are hot, main and the summation. And the granularity of compilation in HotSpot is basically a method. So it improves in when a method switches from one transition to another. But most programs will look more like a curve because it'll be a larger number of methods that are at play. But for an individual method, it really is a stair step like this. If you wanted to see what's going on under the hood, you could run the same program with -XX colon plus print compilation, which will actually show you the just-in-time compilers triggering. And you get a table that looks something like this. The leftmost column here is the time at which the compilation was done in milliseconds since the VM started. The next column is a compilation ID. They're assigned sequentially as compiles are in-queued. Compilations happen in the background, in separate threads, and they won't necessarily finish in order. As you can see here, compiles 4, 3, and 5 sort of finish not in the order they were in-queued. Then we see the method name. Then we see the tier of the compilation. In this case, we see 3, 1, and 4. That refers to the different JITs. We'll talk about why it's not just like 1 and 2 in a minute. Then we see the method name and the size of the method in bytes of bytecode. And at the bottom, you can see highlighted in green the main of this program. Sometimes it's main that gets compiled, sometimes it's sum, but either way, part of the hot loop gets compiled. And two of the main compilations here are a little bit funny. They have this extra % sign next to them, which indicates that it's not a compile of all of main, it's a compile of just a loop inside of main, and that number off to the side is what we would call the bytecode index. Basically think line number of the loop. And so that's what it looks like. Now, reading this output can be a little bit tough, and it gets particularly nasty if you've got other output from the program, or you've got lots of compiler threads, you can get interleaved output. It's pretty ugly. So I prefer to use this tool called JITWATCH, which I've already started running. And JITWATCH can read a log file of all this data, but you can also do some fun things with it. You can open a sandbox and write a tiny program, and you can just run it, and it'll run it with all the right flags. And it will give you a view like this of, say, what actually got just-in-time compiled. So here's the code on the left. In Java, the bytecode in the middle. It's actually doing some rather interesting things like highlighting branches, inline calls, and even showing me the machine code if I've set it all up properly. And for a more complicated program, I could feed it a whole log, and it'll show me all the compilations that occurred, and I can go and drill into each individual one. So if you don't want to do it command line like I'm going to do it today, JITWATCH is an excellent tool to go and play with. What JITWATCH is actually reading is a file called, well, I call it log compilation XML. You produce this by doing unlock diagnostic VM options, log compilation. Those do have to be in that order. You have to unlock first to be able to use log compilation. And it produces this rather gnarly XML file, but it does contain a lot of interesting information that you're not going to get through print compilation or even through JITWATCH. You can see when the individual compiles were in-queued. You can see when they finished. It'll actually print out all sorts of information about optimizations that got applied, and profile data, and some other things that we're going to see a little bit later. It is all there. I'm not going to pretend that this is a user-friendly file format. Okay, so what about these two different JITs? It's a little strange. Well, traditionally HotSpot was composed of two just-in-time compilers, because it was actually two different VMs, a client VM and a server VM. And the client VM's purpose was to do GUI code well. And for a GUI application, what you want is fast startup. No one likes staring at the Eclipse splash screen, as far as I know. Maybe one of you really likes it, but I don't. I don't want to stare at the Eclipse splash screen. That's why I never restart Eclipse. So we want fast startup. But after that, you know, I'm a ploddingly slow human. I barely notice like a 10 millisecond delay. So the code actually doesn't need to run all that fast. And that's actually what the client compiler is designed to do. It compiles very quickly, but it produces relatively slow code. The server compiler is designed for the other case. We're not going to restart this very often. We don't mind if it takes a while to start the server. You know, obviously we don't want to go back to the days of enterprise application servers that took 5 minutes to start, but you know, we can tolerate 5 or 10 seconds probably. So this compiler is slow, about 4 times slower than the client compiler, but it produces code that's, say, 2-fold and sometimes much more than that faster than the client compiler. And the goal here is to serve, you know, a lot of humans on the other side of a server, or even a lot of machines on the other side of a server. So different goals. In Java 8, they tried to basically create the best of both worlds by using both. Using the client compiler, C1, to get us warmed up quickly, and the server compiler, C2, to get us peak performance in the end. But the tiering system isn't just 1 and 2, as we kind of already saw from the log. It's actually 0 to 4. You can think of 0 as being the interpreter. The normal workflow is actually to go to tier 3 first. To know to go from 3 to 4, we're going to need something to trigger it, so there's some counters. And when those counters pass a certain threshold, we go from 3 to 4. There are similar counters to go from 0 to 3. And then C2, the second tier JIT, does all sorts of cool optimizations based on observations about your code. But to get that, we're going to have to do some profiling. We're going to have to instrument the code to get the data. We'll see some of the instrumentation a little bit later, but for now, let's accept that's how it works. And after we've gotten that data in tier 3, we're going to go to tier 4, and that's when we'll hopefully produce the best code. Now, because C2, tier 4, is rather slow, at startup, when a lot of activity is occurring, it's going to get backed up. Its queue is going to be very full, and we're just not going to be able to get to it right away. And rather than having all the overhead of tier 3, in that mode, the system will say, well, let's go to tier 2. Let's not add all that extra instrumentation. Let's just do some counters to see if the method stays hot. And if it does, we'll go to 3 and we'll get the data. And then hopefully by then, the compile queue for C2 won't be so busy. And then there's one more case, a trivial method case. C2 is really good at loops and other more complicated control flow structures. But if you don't have any of that, you don't really need all the overhead of C2. So C1 will actually compile it, say at tier 3 or 2, and it'll go, well, that wasn't very hard. I can handle this. And it will recompile right away in tier 1, which has no overhead of counters or profiling. So contrary to what you would probably expect, your end goals here are to get to tiers 4 or 1, and tier 1 is faster than tier 2 is faster than tier 3. Yeah, but that's how it works. And all of this is basically done at a method level. There are 2 classic types of JITs, a method JIT and a trace JIT. HotSpot has always been a method JIT. It compiles whole methods at a time. A trace JIT will compile a hot line through the code which may span methods. HotSpot can span methods by basically copying and pasting one method into another. It's called inlining, but the granularity is a method. Except for one case, loops. There are a lot of situations like the run of a runnable for a thread where that thing gets called once per thread. If we're only going to compile things that have been called a lot, it would never qualify. So there is also this thing called a loop compilation, or what it's actually called is on-stack replacement, which is a crazy sounding term, but basically the reason the term is what it is we're already running this method. We're running sum. It's running in the interpreter, and so we already have an interpreter frame on the stack, and now we want to just compile time compile just a loop. And once we've done that, we're going to put a machine frame on the stack and copy all the data from the interpreter frame to the machine frame and continue running again. So we're actually changing the execution while it's already on the stack. And that's where the term on-stack replacement comes from. But you can basically think of it as a loop compilation. And for our very simple program, this was important. How many times does main get called usually? 1. You can call it more than that. But most times, it's only called once. And so the only chance we're going to get to switch to machine code is if we compile a loop. The exact when of this happens is not so important, but basically what you should know is every method has an invocation counter, and when a method's been called enough times to pass its invocation threshold, it gets a whole method compilation, and also has what's called a back edge counter, or you can think of it as a loop counter, and when that passes a threshold, we get a loop compilation. But you can also use these two in combination to pass a threshold to compile methods that have been called a little bit and also have loops that run a little bit. Because otherwise, those things might take a really long time to get just-in-time compiled. And that would not be good. Think of something like ArrayList index of. If you really do want to know the thresholds, you can run the VM with print flags final, and it will tell you in grep for threshold, and you can see what the thresholds are, both for Java 8 with tiered compilation or Java 7 without tiered compilation. So here's the simple mental model of what's going on. We start off in the interpreter. After some amount of invocations or loops, we trigger C1. Eventually, C1 gets installed. We start using it. We run for a little while longer, get some more invocations, some more loops. We trigger C2, we switch to it. And that's how our performance improves. And it is a stair step. Here shown going up rather than down, but it is a stair step for an individual method. In aggregate, we're doing this for a lot of methods, and the net effect on performance is more of a curve. Now, I wanted to see how this worked for a non-trivial example. So I actually plotted which compilations were being used over the course of a 80-second run of a benchmark. And you can see this actually goes out to 100 seconds because there's a bit of time to warm up the VM and a bit of time to write out the results of the benchmark in the end. But this is showing all the different tiers of compilation as they're happening. So the blue at the bottom is the trivial methods. You can see we find almost all of them immediately, and they stay compiled. At the beginning when the VM is starting, there's a lot of work for all the compilers to do, and C2 being kind of slow, its queue gets backed up. So then the VM starts producing these tier 2 compilations. Once everything settles down a bit, we won't really produce more of those. So you can see it sort of peaks very early on, 10 seconds into the run, and then drops off quickly. The tier 3s are pretty stable until the end. And then as time goes on, once we get like 20 seconds into the run, we can see a lot of tier 4 compilations, the end goal, have been reached. And it's pretty stable from like 20 seconds to 90 seconds. Why does it go up at 90 seconds? The application changes what it's doing. From about 10 seconds to 90 seconds, it's running the benchmark. And so new methods are getting hot, or they get hot and then they just stay hot. And then at 90 seconds, the benchmark is done, and we're writing out the results. And that requires generating some graphs and writing out files, and a whole bunch of new code gets hot. And that's why we see this rise. We call this a phase change in the application. It was doing one thing, and then suddenly it started doing something else, so new code is hot, and now it needs to be just-in-time compiled. This is pretty typical for any non-trivial application. Okay. That was interesting. But why just-in-time compilation? Why not ahead-of-time compilation? Wouldn't that be easier? Wouldn't that be better? Not necessarily. First off, almost any program consists a lot of warm-up and run-once code. There's a lot of like one-time cache setup or class loading or what have you. And it really happens once and that's it. It's kind of a waste to compile that if you're only going to run it once. You could just run it in the interpreter. And if you look at the history of, say, Chrome's V8 engine, they started off with just having a just-in-time compiler, but over time, they actually did add an interpreter to deal with the run once code, because otherwise they were just producing a lot of machine code that was used once and then never again. And that was just a waste of memory. But there's something more to this. From my perspective, Java is a dynamic language. I know you think I'm insane. You're like, Java has so much ceremony, it's static, I have to use this compiler. Oh my goodness, how could you call this a dynamic language? Well, think about it from my perspective. It is dynamically loaded. It is lazy initialized. It has runtime checking. And it is almost always dynamically dispatched at calls. It really cannot get much more dynamic than that. Okay, we could add dynamic types too, but we got every other type of dynamicism there is. And that actually makes it hard for an ahead-of-time compiler. There are a lot of things that are just tricky. Let's take class loading. HotSpot does lazy class loading. That's not actually mandated by the spec, but that's what it does. And so let's say I have a condition, and this condition has always been true, so the only thing I've ever run is the if part here. I've run class1 get static. I've never run the else condition return class2 get static. So we've never loaded class2, but we've run this method a lot. So we want it just in time compiled. But we haven't loaded class2. We haven't loaded fully half of the code involved in this method. What is the just-in-time compiler to do? If that class hasn't been loaded, what does the just-in-time compiler know about the method, or the class? It doesn't know what fields it has. It doesn't know what methods it has. It doesn't know what parent class it has. It doesn't know its interfaces. It doesn't really know anything other than you think there's a class with that name. That's all it really knows. So what does it do? With this else block, it just says, I give up. It installs what's called an uncommon trap. It just says, I don't know anything about this. I give up. And it makes it the interpreter's job to deal with it. And the interpreter will then try to load the class, and we'll see if we can, in fact, run get static. And of course, this means when you hit this, you're going slow again. You went from C2, which could be running 10 to 100x faster than the interpreter, to now running slow again. And that can cause a disruption in your performance. But it gets worse. Classes must be lazy initialized. This is mandated by the spec. You must initialize a class at the very first static field access, static method call, new of the class, or initialization of a child class. You cannot do it before that. That is a violation of the specification and will break applications. Which is really unfortunate, because, at least for an ahead-of-time compiler it would be, because if I have my class get static, basically what the just-in-time compiler would have to produce is, hey, VM, have I been initialized? No? Okay, please initialize me. Okay, now my class gets static. Ugh. That's a lot of code. It would actually bloat the code size by about 20%. And it would slow down execution by about 5 to 10%. C# actually made this behavior optional. You can decide eager or lazy. But in Java, it has to be lazy. And that makes it hard on the ahead-of-time compiler. It would have to generate a lot more code. And that code would actually be slower than what the just-in-time compiler would produce. Because the just-in-time compiler gets the benefit of running later. By the time the just-in-time compiler runs, most classes have already been initialized. Most. Usually, if I've got a call to my class get static inside of that code, it's already been initialized. or I just haven't been using it. And so at compile time, we can say, hey, VM, is the class initialized? Great. I don't have to worry about it anymore. Just call the method. No overhead. If it's not initialized, oh, well, that's the interpreter's problem. And so we can get rid of this overhead. And we can actually just not produce that code. That's good. But we can only do this because we're running late. An ahead of time compiler, by definition, well, runs ahead of time. As in, before all class initialization occurred. And it would have to check this everywhere. OK, but what if a class fails to init? What would happen then? And what if that class that failed to init was sitting inside a hot piece of code? What do you think would happen? Oh, let's find out, just for fun. We're going to run this example here. I have a main that is going to try to construct 10 million instances of a class called UNINITIALIZED. And I wanted this program to be robust, so I caught throwable inside my loop, just to make sure it keeps running. And of course, this loop is going to get pretty darn hot. But as you can see, this class is going to be rather difficult to initialize correctly. The static block always throws a new runtime exception. Yes, I had to add the if true to get JavaC to shut up and let me always throw a runtime exception. But that's enough. OK, so this will never work. So what's going to happen? The loop's going to get hot. We're going to just-in-time compile it. But the class isn't loaded. So it's going to put in a trap. And then we're going to try to run that piece of code. And we're going to trap. And we're going to go back to the interpreter. But we're going to catch the exception. And we're going to keep going. So the loop's going to get hot again. But we're going to have to put in a trap. And then we're going to catch the runtime exception. And you see what's going to happen here. So here's our program. And it's running. My, that's unfortunate. What is happening here is the lines that don't have the yellow on the end, those are the compiles that are getting done. The ones that have the yellow on the end are where we hit the trap and threw the compile away. And it just kind of keeps going like this, over and over and over again. Could we handle this case better? Yes. Are most of you good enough Java programmers to not make this happen? Yes. So we haven't bothered. OK, actually, we did implement this about a month ago, but not in HotSpot. And if you wanted to, you could actually take this program and go down into the log compilation XML and see that everything I'm telling you is in fact true. You can actually go and find the compile and see that it put out this uncommon trap tag that you see in the bottom left. And it says, at BCI 5, I installed a trap with a reason uninitialized for the class mentioned above. And then you can find another overloaded version of the uncommon trap tag later that is the actual triggering of the trap when we try to run the compiled code. And then that bails to the interpreter. And then the make not entrant is saying, I'm going to throw this compile away. This is going on all the time as your program is running. And this may seem kind of crazy, but this compiling later and doing traps allows us to speculate. We can guess about what's going to be true. We can look at what your program does for a short time in the beginning, and we can say, well, let's assume they're going to keep doing the same thing. At least most of what they've been doing, they're going to keep doing, and let's optimize for that. And again, an ahead-of-time compiler just can't do this. You don't know until you run the code what you're going to do. There are other types of profile-guided optimization we could do, even with an ahead-of-time compiler, but you ultimately have to iterate and compile again. So to refine the mental model a little bit, when we very beginning, when we start running a method, there's a short period where we don't sample the behavior of what you're doing because you do a lot of one-time setup stuff. And that's not interesting. That's not what you're going to do for the rest of time. But after that, we're going to take a sampling period, a little bit in the interpreter and a little more in C1, and we're going to say, we think that's what you're going to keep doing. What you did during that period of time, let's hope that's what you keep doing, and then we'll send that information over to C2, and we'll let it optimize for that. And that gives us some really cool optimizations that let us deal with some of this dynamicism and runtime checking. And that is, in fact, the difference, this profile gathering, between tiers 2 and 3 of C1. One of them just checks for hotness. The other one profiles and gets all this sort of information that informs C2 on how to do these interesting optimizations. But when these go wrong, we are basically going to unjit the code or deoptimize the code. Let's look at an example or two. Null checking. Every access in Java potentially has a null check associated with it, right? I have an array, I check the length. Well, could the reference to the array be null? Sure. Okay, I have to throw a null pointer exception. I'm going to call a method on an object, say hashcode. Could the object you're using be null? Sure, I have to throw a null pointer exception. Now, I'm assuming that you're all good enough Java programmers that you do not throw null pointer exceptions like mad. Please don't dispel me of that notion. I hope that is true. But of course, we still have to deal with this. So I have a program here. And I have a hot method, which I'm going to call on the right. And on the left, I have main. And I'm going to call this method 20,000 times inside a loop to get it just in time compiled. And I'm going to give it the string hello, which is, of course, non-null. And so essentially, I'm going to teach the VM that I don't expect nulls here. In this whole warm-up period that we were running where I was profiling it, you never showed me a null, so I'm going to assume that nulls are probably not going to happen and optimize for that. Then I'm going to kindly dispel the VM of this notion. In the loop on the bottom, I say I'm tempting fate by showing it a null and another null and another null, and we're going to see how it reacts to that. Just by running this with print compilation turned on. All right, so it's running. This time I think I turned off tiered compilation just to make it a little easier to read. But there you go, hot method got compiled under the assumption that nulls were not a thing. And then I tempt fate once. And it has to bail by throwing a null pointer exception, but that's okay. Nothing much happens. I tempt fate again. And the same thing happens again. The third time, VM goes, okay, this person clearly does not know what they are doing. They keep producing null pointer exceptions. I have been dispelled of my notion that this person is a good Java programmer. I need to produce different code to deal with bad Java programmer. There's actually a next level beyond this where it optimizes throwing null pointer exceptions for the really, really bad Java programmers. So if you have really bad colleagues, don't worry, their code is still okay. But it's actually kind of interesting to look at what's going on under the hood here. You would think this call to value.hashcode, it must have if value equals null in front of it, throw null pointer exception. That is, in fact, not what it has. If you wanted to use JITWATCH and go look at the actual machine code, you'd find basically just a straight dereference of memory of RSI, the register that holds value, with the comment, implicit exception dispatches to some arbitrary exception or address. What does that mean? Well, think of this like C code, and think of it as a null. What happens if you dereferences null in C code? It segfaults. Yes, absolutely, and that's what the VM does. It segfaults. Your VM crashes. No, it's installed a signal handler for segmentation violations, and it goes, I segfaulted. I meant to throw a null pointer exception. And this seems crazy, because it's really darn slow when it happens. But because we did it this way, we didn't have to do this if check inside the machine code. The machine code got smaller, just like in the class initialization example. It gets to run faster, we put less pressure on the branch predictor, all sorts of good things happen from this, as long as nulls don't happen often. If nulls start happening often, this is terrible. You got to switch from user mode to kernel mode, back to user mode. It is slow. So if you're dealing with a bad Java program where this does not work, then you want to go and do the explicit if. And that's in fact what it will do. There are other variations on this. We can take an example like this. We got a hot method on the right, and we're going to train it that thing is always null. And when thing is null, we print out the empty string. When thing is not null, we're going to do something radically different. We're going to print out the empty string. But what is going to happen here is it's going to say, well, thing has always been null, so I'm just not even going to bother to compile the else block. And so once we get to the bottom loop, after I've set thing to non-null, we're now violating the expectation that's been built up as the program was running. And it's going to have to correct that. This time with tiered compilation turned on, this is the output you would get. You see tier 3, C1, tier 4, C2, speculating that the else will never happen. Then the value is in fact non-null. It bails to the interpreter. And it actually throws away the compile. And now we go through 3 and then 4 again, and it's now learned from its mistake. It said, that else block actually does happen. I should compile both of them. Again, if you really want to, you can go and look at the log compilation output on the right. You will find in the compile, you'll see branch target BCI is this, taken 0 times, not taken 5,800 times. Probability this will occur is never. It's actually the inverse of the test. And I'm going to do an uncommon trap called unstable if. Previously, this was called unreached. So it depends on the version of the VM you're using. And then you can see hitting of the trap. And then subsequently, it will recompile. And if you looked again, you could find that the branch data had been updated to say this was taken, 2 times, or however many it is. And this seems crazy, right? Because after all, the if and the else were the same. The outcome is printing out the empty string in both cases. And what did we really optimize? The if we still have to actually check that condition. If you look at the code in the lower left here, we still have to check it. So what did we gain? In this case, honestly, nothing. This is silly. But there are situations where we would gain something. So imagine condition is always true, so we're always going left, and x is 100, versus if condition was false, we go right, and x is -1. And beyond that, there's a check that says if x is greater than 0. Well, by discarding the right half, we can now actually say, x is always greater than 0, and we can start to optimize. It's not the first if, it's everything that follows from that. We do start to get significant gains. Historically, HotSpot's actually gone back and forth on how aggressive to be about this optimization. Okay, so let's revise our mental model of what's going on once more. We start off, we go from C1 to C2. we're a little over-aggressive. We've made some speculations that aren't quite going to hold. And when that happens, you're going to plummet back down to the interpreter, and you're going to go up again. And when you do that, you're going to do some additional sampling, additional profiling to learn what all the behaviors of the program are, and then hopefully you'll stabilize. Obviously, if you have a class that you can't initialize, you're never going to stabilize. Well, I guess it stabilized in some sense, right? Not in a good way. And then we can actually use this to drive really aggressive optimizations around, say, dynamic dispatch function calls. Everything in Java is dynamically dispatched. So what we actually do is we profile all the types flowing through there. As it turns out, most of the time you only use one type, 90% of the time. 95% of the time you use 2 or fewer types. 5% of the time you get greedy and use 3 or more. And so we'll optimize for that. We'll actually take that and turn it into, if it's this type that you used really often, just inline the code to it directly. Else if it's that other type that you use a little less often, inline that code too. Else, you can probably guess by now, uncommon trap. And if that fails, then we're going to go back to just doing a virtual call. And this is something that you just couldn't do with an ahead-of-time compiler. You have to actually go and profile the application first, and then feed this information back into a compiler. And so the JIT code can actually run faster than the ahead-of-time code could have. And well, how much do these things occur? Well, that benchmark I showed you earlier, this is a plot of the deoptimizations over time. So most of them, we get them out of the way pretty quickly. We don't have a lot of sampling information about those very first compilers we do, and we make kind of a lot of mistakes. And then when we start doing new stuff, like around second 15, 20, when the benchmark really starts running, we've got some new code, we make a few more mistakes. It quickly settles down and we don't really have much more. And then when we start running some new code again, when we're doing the benchmark output results at second 90, it spikes again. So each piece of new code, there will be some failed speculations, but it usually settles down pretty quickly. Unless you've got an uninitialized class, right? Okay, but how much does any of this really matter to you? Well, the speculative optimizations absolutely do matter to you. They're easily at least 25% for almost anything you're running. Often way, 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 way more than that. Particularly if you've got like a dynamic call inside of a loop, it's like 1,000%. So you probably want this if you want your Java code to run quickly. And that sort of implies you do actually want a JIT or some sort of profile-guided optimization. But it's certainly not without its downsides. Most of the time when we hit one of these uncommon traps, not only does the thread that hit the trap bail to the interpreter, the thread that's doing the anomalous behavior, the thread that's hitting nulls or use that third type or whatever, but when we hit the trap, we also throw away the compile. We lock out access to it. And so new callers to that compile, they all also basically end up bailing to the interpreter. And so now there's this brief slowdown in your application. It's not huge. Your application didn't stop, but you went from going 100 miles an hour to 1 mile an hour again. If this happens to a hot method in your system, on a modern Intel chip, it's, say, 25 to 50 milliseconds of disruption, depending on the type of trap and how it's handled. It's not huge, probably smaller than most of your garbage collection pauses, but it is there. And it's actually maddeningly hard to measure. It doesn't show up in a GC log. Sure, it shows up in a log compilation XML, but you got to know that the method is hot. You can really only measure it externally in any real way. But it does occur. And if you had, say, microservices and, say, one microservice fronting another microservice, and this one does a new behavior, which triggers a new behavior in this one and this one, that could compound. But ultimately, it really depends on what your goal is. Is your goal startup time? Great. Maybe just use an interpreter. Sounds crazy, but it's not actually a terrible idea. That's what Android did. That's what the Hermes VM is doing from Facebook for the Facebook application on iPhone. They just have a really good interpreter. starts really quickly. Doesn't run fast, but it starts up really quickly. Maybe your goal is peak performance. Well, then you want profile guided optimization. You want a just-in-time compiler or some other speculation and feedback system. Maybe your goal is first response. Maybe that also means peak. Maybe it doesn't. Maybe an ahead-of-time compiler is the right choice. Maybe you want predictable performance. Okay, an ahead-of-time compiler is fine. It might be slower, but it'll be nice and predictable. It all depends. There is no one right or wrong answer to this question of what the best type of compiler or execution mechanism is. What Oracle is actually doing with their ahead-of-time compiler is they have two modes. They have a non-tiered mode, produces relatively conservative code that has to have initialization checking, doesn't get to do all these cool speculations, but it's rock solid stable. And then they have a tiered mode. It starts off in that same stable mode, but then it switches to profile gathering, gets some data, and then goes into the speculative mode. They have both, because there's not one right answer to this story. What we've done at Azul is we've actually done something a little different. We take all that profile information and information about what got compiled, what was hot, and we do something brilliant. We put it in a file. I know. Yes, this is what I get paid for, putting things in files. And then we read that back in again, and we use that to basically start from the same spot. Not exactly, it's a lot trickier than it sounds, but we start off basically running at peak, although it's not exactly as good, but it's close. The first transaction that hits our system is about 3 milliseconds slower than the second transaction, and that's at peak speed. So this does actually work pretty well. But every approach has its pros and cons. But in fact, it actually gets worse. I told you it could get more dynamic. I lied. It can. There's this notion in JavaScript that eval is evil. I'm semi-inclined to agree. Guess what? Java users, you are the most heavy users of eval in the world. Okay, it's not called eval, it's called bytecode, runtime bytecode generation. And they're like, I don't do that. What are you talking about? Oh, but you use persistence libraries that do it. Or you use an aspect-oriented programming library that does it. Or a rules engine that does it. Or Spring, or Hibernate, or Reflection, or, okay, we're at fault too. We added lambdas to Java, and we used runtime bytecode generation. How do you ahead of time compile something that isn't there? It's really tricky. And in fact, this is something that the AOT project for Oracle is having to deal with. They are having to change how they handle lambdas because the current scheme is really not very friendly to an AOT. Now, I think this isn't so terrible. It's not, we evolved to use what the VM was good at. Not a surprise. But that is where we are today. All right. I hope you learned something about the VM. I hope you found this all interesting and have a little bit better understanding what's going on under the hood and how it affects you. If you found this interesting, please go play with JITWATCH. And if you'd like to learn more, well, really you have to go read the blogs of the people who work on this. So you can go read the blog of Alexei Shipilov, who used to be at Oracle, who's now at Red Hat. You can read the Java Specialist newsletter, or you can read my former colleague's blog, Nitsan Wukart, Psychomotic Lobotomy Saw. They're all great references. If you found this interesting, please go learn some more. And thank you all very much for coming.